Hello, everyone. This presentation covers a Computational Fluid Dynamics (CFD) simulation, comparing indoor temperature profiles and air movement. We specifically analyze two scenarios: a traditional wall-mounted radiator versus an underfloor heating system. The simulation was performed in a room measuring 4.0 by 4.0 meters, with a ceiling height of 2.8 meters. The model includes two windows and one door. In the first scenario, the heating element is positioned as a wall-mounted unit opposite the door. In the radiator configuration, heat transfer is primarily driven by convection. As the air is heated, its density decreases, causing it to rise toward the ceiling. It then cools along the walls, sinks, and flows back across the floor to the heat source, creating a continuous circulation pattern. Furthermore, the CFD model accounts for thermal radiation, which contributes approximately 20% to the total heating. Note that the windows and door exhibit higher thermal transmittance compared to the insulated walls. For the second scenario, we simulated an underfloor heating system, where the floor serves as a homogeneous heat source. The heat rises uniformly from the ground towards the ceiling. In this case, convection remains the primary driver, but due to the lower surface temperature, the radiative component and the flow profile differ significantly from the wall-mounted unit. The computational grid was generated using GMSH. This mesh structure allows us to capture the gradients accurately. For visualization purposes, the volumetric room mesh is hidden here to focus on the surface discretization. Comparing the setups. First, we compare the different scenarios in this schematic figure, before we go to inspect the results of the CFD calculation. The left figure shows wall heating and the right figure shows floor heating. Now we inspect the calculation results. Wall heating. On the left, we see the isothermal lines. With a source temperature of 50 degrees Celsius, 323 kelvins, the heat rises sharply to the ceiling before dispersing. The windows and door are clearly visible as cooler zones. Underfloor heating. On the right, the distribution is much more homogeneous. With a surface temperature of 25 degrees Celsius, we observe a steady vertical temperature gradient, where the lower part of the room remains warmer than the upper section, the inverse of the radiator profile. Looking at the velocity magnitude isovels, wall heating, we observe high-velocity air movement near the radiator, resulting in a distinct circular vortex. Underfloor heating, the flow is significantly more balanced. While the center of the room stays warm, the highest velocities are localized near the sources of cold air infiltration, the door and walls. The simulation yielded three key findings. Temperature requirements. To maintain a mean room temperature of 20 degrees Celsius, the radiator required a flow temperature of 50 degrees Celsius, whereas the underfloor system only required 25 degrees Celsius. Energy consumption. In both cases, approximately 1,400 watts were needed to maintain equilibrium. The energy demand is identical for both methods under these specific conditions. Efficiency advantage. The primary benefit of underfloor heating is the significantly lower operating temperature, 25 degrees Celsius versus 50 degrees Celsius. This allows for a much higher system efficiency, particularly when integrated with modern heat pump technology, as the required temperature lift is minimized.